Welcome. What we're going to do is we're going to walk through how to write an electron configuration. First, the most important thing that you'll need is a periodic table. Here I have my periodic table that I'm going to use today, and it has electron configuration endings written on it already. The element that we're going to look at first is selenium. Selenium is located right here on the periodic table. It's element number 34, Se. And since it has the atomic number of 34, if it were a neutral element or a neutral atom, it would have 34 electrons as well. So you can see here it says 4p4. That is the ending of the electron configuration for selenium. We're going to write the complete electron configuration. To do that, I'm just going to go ahead and box the different parts that we're going to need in order to write the electron configuration for selenium. What we're going to focus in on is the configuration for helium. We're going to focus on the configuration for beryllium, for neon, for magnesium, argon, calcium, and zinc. The reason why we're going to use these in constructing the electron configuration for selenium is because all of these are the last elements in their respective blocks. And that's pretty much the name of the game. You'll include any element at the end of each block until you get to the actual element you're looking for. So let's write it. Starts with helium, 1s2, beryllium, 2s2, neon, 2p6, magnesium, 3s2, argon, 3p6, calcium, 4s2, zinc, 3d10, and then we end with selenium, 4p4. All right. So in order, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Now what I'm going to do real quickly is I'm going to interpret that electron configuration and show you what the parts actually mean. So for this, when we look at our exponents here, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 4 is 34. So this exponent, it's going to tell us how many electrons there are in each of these, okay, in each of these sections. On the other hand, when we look at our letter, the S's, the P's, and the D's, what do these represent? These are telling us our shape, and it's the shape of our orbitals. Okay. In chemistry or physical science, an orbital is just it's the same thing as the shape of our electron cloud. All right. So shape of orbital or electron cloud, where an s orbital or a s cloud is spherical in shape, and a P would be dumbbell or balloon in shape. All right. And then the last piece of our code, the big number out front. This big number out front, I'm going to call a coefficient. 1, 2, 3, 4. What does that tell us? This last piece tells us the energy level where these electrons are found. In energy level, in basic terms, we can think of this also as how far away we are from the nucleus. Okay, how far away from the nucleus? 1, meaning we're very close to the nucleus. 4, we're further away from the nucleus. All right. So if we took a little snapshot, 1s2 versus 2s2 versus 3s2 versus 4s2. They both, all 4 of these have 2 electrons in them. They're all spherically shaped, but 1, 2, 3, 4, they are increasing in distance away from the nucleus. These are the closest to the nucleus, these are furthest away from the nucleus. So this is how you write an electron configuration. This is what each part of the electron configuration is representing. So hopefully that clarifies some things. What you'll end up doing is writing the electron configurations of several different elements. And this code is giving you a picture. It's just you have to interpret that code. Just try to imagine what it would be like if we drew a picture of 34 spheres and balloons all stuck together. It'd be a very cluttered picture, and the resolution would not be good enough to see those electrons. So that's why we write it in code form, and then we interpret that code from there. That's all. Hopefully it was useful and helpful. Good luck.